This is part 5 of the Module 4 lecture. In this section, we're going to talk about independent events and how to calculate their probabilities. All right, in this case, two events are independent if the occurrence of one event does not affect the probability of occurrence of another event. Now, again, I didn't talk this when I talk about the three types of events: the complement, the joint, and the union of events. And this is because this has to do with the probability, not with the outcomes of one event with respect to the other. So if we have independent events, that means that if we condition on a particular event and then we ask the probability of another event, well, because they're independent, the conditioning will not affect the probability of that event. More specifically, let's say we have events A and B, and we say that those events are independent. So if I wanted to calculate the probability of A given B, well, B has no influence on the occurrence of or doesn't have any effect on the probability of occurrence of event A. So this will be simply the probability of A, or vice versa. If we want the probability of B conditioning on the event A, well, this be just the probability of B, because conditioning on A does not affect the probability of occurrence of B because they are independent. Let's look at some examples to see what this means. All right, sometimes, and I have two examples. The first example deals with the situation where the procedure to perform the experiment guarantees independence. One good example that is easy to relate to is that of flipping coins. And the flips of a coin are independent of each other, because when you flip the coin rotates randomly many times. And again, I'm assuming that we're using a fair coin. That means that either side is equally likely, so there is no preference for one side, and the flipping does not favor any side. So in that situation, if I flip a coin and I get a head, well, the probability of getting another head in the next flip is the same. It doesn't matter what I obtain in the same flip. I'm repeating the experiment, and the way I perform the experiment guarantees that the second result is completely independent of the first result. So for example, here I'm saying the probability of head in the second flip, given that I obtain a tail in the first flip, well, that's just the probability of the head in the second flip, and it's 0.5. So whatever I obtained before does not affect the probability of obtaining a head in the second flip. Similarly, if I'm interested in the probability of a tail in the second flip, given that I saw a tail in the first flip, well, it doesn't matter that I saw a tail in the first flip. The probability of a tail in the second flip is 0.5. So again, this is an example where the performance of the experiment guarantees the independence of the outcomes of the experiment. There are other situations where we don't know if the events are independent or not. So, and then in those cases, we need to demonstrate that these conditions exist. So let's look at this example. Again, in this example, it's a contingency table. 2,000 randomly selected adults were asked whether they ever have shopped on the internet, and the results are here. So you have gender, male and female, and then you have people that shopped online and those that never shopped online. And there are 2,000 of these people. So the question is, are the events shopped and female independent? Well, we don't have any knowledge or explicit knowledge that tells us that they are independent or dependent. We don't know. So this is a case where we have to use the data that we obtain to validate that in this particular case, the probability that shopped online is conditioning that the shopper is a female. Well, it's just the probability of shopped online. So if I find that the conditional probability of shopped online, given that the shopper is a female, and that's exactly equal to the probability of shopped online, then I say that the two events are independent. Alternatively, we can demonstrate it this way. So we can calculate the probability the shopper is a female, conditioning on having shopped online. And if that conditional probability is equal to just the probability the shopper is a female, again, we demonstrate that these two events are independent. So either way, you can do these calculations and demonstrate independence if you get this equality. So let's look. Let's use the data and calculate that. All right, let's look at the first case. So we're going to define the events A, shopped online, and B, the shopper is a female. So let's calculate the probability that shopped online given that the shopper is a female. So we're conditioning on a female. So that conditional probability is 200 females shopped online out of that total of 800 females. So that probability is 0.25. Now let's calculate the probability of shopped online. So here we don't care about gender, we just want to find the probability that shopped online. And that's 750 out of 2,000. That's 0.375. You find that these two probabilities are not equal. Therefore, the probability of shopped online and shopper is a female are not independent. They are dependent events. And you can see that depending on which gender you ask questions about it. For example, males seem to have more people shopped online. So again, we don't know a priori if these two events are independent. So we have to demonstrate it by calculating the corresponding probabilities. And by calculating the conditional probability and the marginal probability, we find that they are not equal. Therefore, these events are not independent. Now, if you decide to go the other route and now show that the condition on shopped online, then the probability that the shopper is a female, given that she shopped online, is now we're conditioning on shopped online. So right here, that's a red square. So now that's 700, and they're females, so there's 200 females out of 750 that shopped online. That's 0.2667. And then the probability of being a female, so now we have 800 out of 2,000 being female shoppers. That's 0.4. Again, these two numbers do not match. Therefore, we can conclude either from the first calculation or the second calculation that the events shopped online and female are not independent. So this is an example where you need to demonstrate independence because there is the way in which the experiment was performed does not imply independence. We need to verify it through calculations, but demonstrating either of these two conditions right here, either this condition or this condition, as we did in that example. All right, so now with this, we have discussed all the different probability calculations, and now we're going to talk about the multiplication rule. Just to keep things separate, I'm going to discuss this in the next segment because we need time to explain.